All right, so the third and final reaction we're going to deal with that involves CYP450 is going to be epoxidation. So epoxidation, you're going to start out with a double bond. You've got P450. Here we have the oxine atom. The oxine atom is actually the thing that gets incorporated into the epoxide. And once you have this epoxide, it's pretty reactive. Okay, so first of all, good things, electron-rich double bonds. P450 just loves electron-rich things because this oxine atom right here, it's electron deficient. Second thing is you're probably going to be dealing with epoxidizing certain aromatic systems. It's best to epoxidize the double bond that preserves as much aromaticity as possible. Okay. Also, when it comes to opening up things, you want to try and preserve as much aromaticity as possible, because breaking up an aromatic ring system, there's an energy penalty for that. It's not thermodynamically favorable. So these epoxides are susceptible to being opened up. Okay. First thing, nucleophilic attack. Okay, nucleophilic attack could be either good or it could be bad. If it's GSH, that's good. Glutathione is protective. And then what happens is you can metabolize it via a bunch of different enzymes and excrete it from your system. If it's your protein or DNA, that's bad because you get the carcinogenic effects or you get the immune response. Okay, second thing you can do is NIH Shift. The NIH Shift is an SN1-like mechanism. So you have an SN1-like opening of the ring, and then you're going to have a shift of, you could possibly have a shift of the hydrogens, and this is going to result in just one OH resulting, being attached to the epoxide. Okay. In contrast, nucleophilic attack is an SN2-like mechanism. Okay. And then a hydrolase, you're going to get 2 times OHs attached. You're going to add water to there to open up the ring. Okay. Now, the one that can get kind of confusing is the NIH shifts and determining, do I add ortho, do I add meta, or do I add para? Okay. And the thing that's going to guide ortho, meta, or para is going to be the stability of the SN1-like transition state, and also whether or not you have an electron withdrawing group or an electron donating group. So let's say we have an electron withdrawing group. There are 2 possible sites where you can open up the epoxide. You can open up the epoxide here in red, or you can open up the epoxide here in orange. Okay. First, let's deal with if you open it up at the meta position. Okay. If you open up at the meta position, what I like to do is I just think once you open that up, let's push one of these electrons or one of these double bonds, the electrons in the double bond, and notice that we generate a positive charge right next to the electron withdrawing group. That's not good. Okay, it's not favorable. So opening it up at the meta position and giving you a para-hydroxyl group, that's not going to happen. Okay, whereas if you open it up at the para position and generate a meta oxygen, what happens when you push this adjacent double bond is you're going to have the positive charge that's 1 carbon away from the electron withdrawing group. Okay, still not the best option, but out of the 2, it's the better option between the 2. Okay, so we're going to open up at the para position, and the OH is going to be at the meta position. Okay, that's what happens when you have an electron withdrawing group. Following the opening of the ring, you can have the actual NIH shift, and then you can also have the keto-eno tautomerization. And when the resulting thing is going to be regenerated aromaticity, you're going to have an OH at the meta position, and you have your electron withdrawing group right there. Okay, so electron withdrawing group, add to the meta position. On the other hand, if you have an electron donating group, we still have the same 2 options. Okay, going down, opening at the para position and giving you a meta oxygen, we have a positive charge that's ortho to the electron donating group. Compare that to if you open up at the meta position. If you open up at the meta position, your hydroxyl is going to be at the para position, and then you push the electrons, and notice that the positive charge ends up right next to the electron donating group. We didn't like that with the electron withdrawing group because that's bad, putting a positive charge next to electron withdrawing. If you have an electron donating group, however, what you can do is you can stabilize it by, well, donating electrons. And the important resonance structure that's going to develop is going to be this one. Okay, so you're going to have the electron donating group, and that helps stabilize the opening up the ring at the meta position and giving you the para adduct. So what's going to happen with the electron donating group is you're going to add para, okay? Or you're going to have the OH at the para position open up at the meta position. You're not going to open up at the para position, okay? Also, if you have the epoxide on another, or not at this distal location, but if you have it right on the side, it could also be added to the meta, or not the meta position, sorry, the ortho position. Okay, it could also be added to the ortho position. Just draw the resonance structures. You're going to have a similar resonance stabilization via the electron donating group. Basically, put the positive charge, use the form that puts the positive charge next to the electron donating group, and that's going to be the para or ortho position, depending upon where the original epoxide was going to be. Okay, and then following the opening of the ring, you're going to again do the NIH and the keto-enol. I'm not going to write the steps in there, but the resulting product, you're going to have the OH. That's going to be para to the electron, not withdrawing, but electron donating group. Okay, so if you're ever confused about like which way it's going to add via the NIH shift, you could memorize it, or you could also look at the resonance structures. Try to pick the resonance structure that puts the positive charge next to an electron donating group. Try to pick the resonance structure that puts the positive charge not next to the electron withdrawing group. Okay, so there we have it. That's the regioselectivity of the NIH shift, depending upon electron withdrawing or electron donating substituents.